Hello everyone. Have you ever heard of an aluminum tubes piano? Have you ever understood how a piano works? Do you really know how to make a piano to generate a pitch? Today, we are going to introduce you what our final handmade instrument is and how it will work to not only generate a sound, but to perform a chorus with an octave.
Hello everyone, we're Group E. We're going to introduce our project, Aluminum Tube Piano. Since the requirements for the project is to play in chords instead of single notes, our instrument design is based on the idea of the outer structure of organ. We simplified it for easier operation, since organ is too complicated, and came up with the idea of using short, solid metal tube to produce sounds. We use aluminum tube because it is easy to cut and produce sounds easily by simply heating it, and it can be constructed with a small volume, which makes it less complicated compared to an actual organ or the string on the piano. Moreover, we construct a keyboard which produces sounds ranging with one octave, according to the Pythagorean octave rules. We create an octave by 8 aluminum tubes with different specified lengths and hit them with our handmade hammer. And by pressing 3 keys simultaneously, we produce chords like pianos do. However, since the structure of a real piano's keyboard is way too complicated, we came up with the tube plan of making hammer on our own in our midterm presentation. Eventually, we select the first method of revised hammer structure with an improved version of it, and we'll explain that in detail in our practical realization part. And this is the whole idea of the instrument structure.
In simulation, we first want to calculate the velocity of our aluminum tube. We take Y as the Young's modulus of elasticity of aluminum, and ρ as the density of aluminum. From our research, Y equals 1.6 times 10 to the power of 11 Newton divided by meter squared, and ρ equals 2,500 kilograms divided by meter cube, respectively. Then, from the equation of V equals the square root of Y divided by ρ, we get the velocity of sound traveling in aluminum tube. And from the equation that lambda equals length times 2 divided by n. In this simulation, we want to calculate the fundamental frequency, so we set n equals 1. We can calculate the wavelength of our 8 aluminum tubes with different lengths according to Pythagorean octave. We then print out the calculation of the wavelength and frequency below. Eventually, we print out a graph of length versus frequency. From the graph, we can tell that when length increases, the frequency decreases. Especially when the length increases double, the frequency decreases by half. Later, we will explain the correlation between frequency and the notes of our instrument.
After simulating frequency of metals of different lengths, we would like to use sine wave to generate sounds and waveforms with different frequency we've gotten previously. First of all, we've built a JSON file with notes name and corresponding frequency so as to simulate each note with its name. And this is the file. Secondly, we construct a class note, which is used for generate a single note at one time. This is notes, class notes. Last but not least, another class tone is built for playing a harmony by inputting the notes wanted. This is class tone. By the way, both functions of class note and tone are implemented by the module Pygame. Finally, our main function consists of three major parts. Single notes with given frequency and amplitude input, also their composed waves, and single notes with note name input, and some harmony chords. And let's start our simulation. And that's all of our simulation.
Okay, here's the math part. We want to look for the impulse force hitting the aluminum rod. We see we have a key and hammer system, and the hammer hit the metal rod to produce sound. I do some research and found wave function, but it's kind of like two derivatives, the dt and dx. But we know sound is a time domain function. So here we just look at the dt part rather than the dx part. So to calculate the mass, first we assume the aluminum rod is a mass spring system, so we can know its vibration. Second, we assume it just vibrates at one direction, so we only calculate 2 dimension, not 3 dimension. Third, since it's kind of fixed at 2 ends, we neglect gravity. So this is mass spring damping function from textbook. Here m is mass, gamma is damping coefficient, which is kind of resistance, and k is spring constant. This is how it comes up. By the equation above, we know y double prime is acceleration, y prime is velocity, so F equals ma equals negative ky minus gamma v minus mg. But we neglect the gravity, so mg doesn't appear here. By differential equation, we get the position function of t, like this. But we have a fixed end, which is elastic band tied on it to keep it stable. I do some research on the internet. I found this article called Reconstruction of Piano Hammer Force from String Velocity. It gives us a function like this. In this model, the piano string is rigid fixed at 2 ends, which is similar to our project. But this wave function is a partial derivative function. It is beyond our knowledge. If we can solve it, we may know the precise function of the rod motion.
Then is our practical realization. First, this is our inspiration in how we plan our instrument to be like in the midterm demonstration. Although we have tried to use a 3D printer to get our work done, the money and time needed just became practical for us. Therefore, we swipe our minds into only using the materials that are easy to get in our daily life. It didn't cost a lot of money to realize our idea. Here are the materials that we needed. For the most important thing, in fact, we need the aluminum tubes to generate the pitch for an octave. Then, we need some cardboard to make the keyboard, and other materials like the paper that is thicker from the gift box package, erasers to kind of rebound our hammerhead, coins to knock the tubes and make sound, tapes, ropes, some rubber bands, popsicle, and wooden sticks. This is our keyboard structure. Though it's easy to know how a piano keyboard works, to make it through paper and cardboards, we have to deal with many problems, like making the sound loud enough, fixing our hole sets, making it bounce back automatically, and other problems that will result. For the sound problem, we substitute coins for sticks to knock the tube because two metals will produce a bright sound other than wood will, and that is what we definitely needed. Distance also matters, so we have to keep the right things in the right place. Next is to make it automatically bounce back. The thing that connects the base and our hammerhead is quite important, and this is how we made it by steps. Without this, if the keyboard was pressed too hard, the hammerhead will just collapse and won't be back again. So they are necessities that the handmade keyboards need. The last step is to fix and assemble our tubes and keyboards. We choose to use rubber bands and sticks to make our tubes sturdy enough and good to align with the keyboard keys. Then do some little adjustments to make the whole instrument more stable. And this is how it looks in the end. Here are some clips that convert to GIFs of our instruments working. And this is our end of the presentation. Thank you.